So imagine strapping an entire skyscraper to like a patch of heavily reinforced concrete.
Right.
You hollow out the core, fill it to the absolute brim with hundreds of tons of deeply frozen, highly volatile explosives, and then you just ignite the main engines at the bottom.
Just light the fuse and step back.
Exactly. And the acoustic energy generated in those first few milliseconds, it's so profoundly violent that it doesn't just produce sound. It produces physical pressure waves that can literally melt acoustic dampeners.
Oh, yeah. It'll turn solid concrete into shrapnel if you're not careful.
Right. And the exhaust heat channeling into the trench below hits temperatures that can liquefy structural steel. So you're taking this machine, which is specifically designed to break the bonds of Earth's gravity, you throttle it to maximal power, and then you use these massive steel clamps to hold it by its ankles.
Just forcing it to stay completely stationary.
Yeah, that is the visceral, kind of terrifying reality of a rocket static fire test.
It really is. I mean, the physical forces at play during that hold down period they're almost difficult to fully conceptualize. It's this crazy crucible where extreme thermodynamics, fluid mechanics, and material science all just collide at once.
And when it works, it's amazing, right?
Oh, absolutely. When the clamps hold and the engine shut down nominally, you've validated the whole system. But when the structural integrity fails, or like a localized anomaly propagates through the vehicle, well, that stationary skyscraper detonates.
It ceases to be a machine.
Right. It instantly becomes one of the most spectacular, high-yield kinetic events in modern engineering.
Which is exactly what we're pulling apart today. We are decoding the anatomy of those massive ground explosions, and we're using a really incredible stack of sources for this deep dive.
Yeah, we've got some great material today.
We do. We're looking at the historical context laid out in John D. Clark's classic Ignition, an informal history of liquid rocket propellants. We've got the rigorous physics detailed in the textbook Rocket Propulsion Elements.
The Bible of rocket engineering, basically.
Truly. And primarily, we are tearing into a cutting-edge, highly detailed research report from May 2026. It's titled OGI, or OLDI, for our English listeners, Rocket Static Fire Explosion Analysis.
And that report is just phenomenal.
It really is. It specifically isolates the microscopic technical roots of these pad failures. So we're talking propellant leaks, seal degradation, and the engineering philosophies driving the fixes, like redundancy and upgraded materials.
Because, the 2026 analysis forces us to look past the giant macroscopic fireball. It makes us examine the microscopic origins.
The tiny stuff that actually starts the fire.
Exactly. The report synthesizes data from space programs all over the globe to show that these massive explosions, they rarely stem from a single catastrophic design flaw in the main combustion chamber itself.
Right. It's usually something way less obvious.
Yeah. They almost universally originate in the margins. The interfaces, the fluid delivery networks, the O-rings, and the control logic.
Okay, let's unpack this, because I actually want to challenge the whole premise of the test itself before we get into how things fail.
Okay, let's hear it.
We live in an era of unprecedented computational power, right? We have finite element analysis models with tens of millions of nodes.
Oh, yeah, the modeling today is incredible.
It is. We can run computational fluid dynamics simulations that model the behavior of every individual droplet of liquid oxygen as it enters an injector plate. So with that level of predictive mathematical modeling, actually lighting the rocket on the pad feels almost archaic.
I mean, I see where you're going with this.
Right. Why are we still risking a $50 million vehicle in a physical test when a supercomputer should just be able to tell us exactly how the metal will behave under stress? It's like testing a suspension bridge by driving 1,000 tanks over it before letting civilian cars cross.
That's a fun analogy, but here's the thing. A mathematical model is, by definition, a simplification of reality. And rockets operate in this wild regime where microscopic, unmodeled variables compound into catastrophic failures.
So the models just can't catch everything.
Exactly. Rocket Propulsion Elements addresses this limitation directly. Like, you can model the thermal stress on a turbopump bearing, sure, but it is exceptionally difficult to model the exact harmonic resonance of that bearing when it's simultaneously subjected to cryogenic temperatures, 5,000 pounds per square inch of fluid pressure, and
the acoustic vibration from the exhaust,
yes.
right?
Yes, the chaotic acoustic vibration of the engine exhaust bouncing off the concrete trench and blasting right back into the engine bay. The static fire test forces all of those coupled thermomechanical interactions to occur simultaneously.
It exposes the unknown unknowns.
Precisely.
So an explosion on the pad, while it looks visually disastrous for the PR team, is analytically a success.
Analytically, yes, it is the successful capture of a critical vulnerability.
Because you forced a fatal anomaly to reveal itself on the ground where you can, sweep up the slag and analyze the telemetry.
Right, rather than losing the vehicle, the payload, and all the evidence somewhere over the Atlantic Ocean at Mach 15. Because if that specific harmonic resonance had shattered a methane feed line at max Q during flight, you lose everything. And your telemetry cuts out precisely when you need it most.
That makes total sense. And, this struggle to contain the violence of ignition, it's practically the defining narrative of early rocketry. If we look at John D. Clark's ignition, the engineers in the 1950s and 60s weren't dealing with supercomputers failing to predict harmonics.
Oh, not even close.
They were dealing with fundamental chemistry that actively wanted to destroy the test stand.
Clark's accounts of working with hypergolic propellants are just fascinating. Hypergolics, for those who might not know, they ignite spontaneously upon contact with each other.
Which is handy because it eliminates the need for complex ignition hardware.
Right, but they are notoriously unforgiving.
Unforgiving is a polite way to put it. Clark writes about testing chlorine trifluoride, which is an oxidizer so aggressive it can spontaneously ignite glass, sand, and, like, asbestos.
Yeah, things that are literally used as fire retardants.
Exactly. And he notes that the earliest testing apparatus for these crazy chemical combinations wasn't some heavily instrumented thrust chamber. It was literally, and I quote, an eyedropper, a small beaker, and a finely calibrated eyeball.
Which is just terrifying because the big risk there was the ignition delay.
Right, the timing of the chemicals mixing.
Yeah. In a hypergolic liquid rocket engine, the fuel and oxidizer are injected into the chamber simultaneously. The physical mechanics of that mixing are critical. If the two liquids contact each other and ignite instantaneously, like within a microsecond, you get a smooth, continuous burn.
But what if they don't?
Well, if there is a chemical hesitation, if the liquids pool in the chamber for even 5 or 10 milliseconds before igniting, the result is totally devastating.
Because in those 10 milliseconds, the turbopumps have already forced another 100 pounds of highly reactive liquid into this tiny, confined space.
Exactly. When that pooled mixture finally does ignite, the volume of gas produced expands at supersonic speeds.
So it's not a burn anymore.
No, it isn't a burn, it's a detonation wave. The internal pressure of the chamber spikes to a level that vastly exceeds the tensile strength of the metal, which results in what Clark dryly refers to as a demolished motor.
Just blown to pieces.
Yep. The historical solution involved expending countless T-motors, which were just these simple, nozzle-less, heavy steel pipes, just to map out the microsecond timing of the chemical reactions. Blowing them up was just a guaranteed part of the development cycle.
Well, we've obviously moved far beyond eyedroppers and T-motors today. But the 2026 report clearly states that the fundamental challenge really hasn't changed, only the complexity of the plumbing.
That's a great way to phrase it.
The report identifies propellant leaks and seal failures as the dominant technical root of modern static fire explosions. And here's where it gets really interesting, because I want to drill down into the thermodynamics of
Oh, this is the best part.
We are pumping liquid oxygen at minus 297 degrees Fahrenheit, or liquid hydrogen at minus 423 degrees Fahrenheit, through these intricate manifolds. And they are located inches away from a combustion chamber burning at 6,000 degrees.
That thermal gradient is the ultimate engineering nightmare.
It's like trying to plug a fire hose with a piece of rubber that is simultaneously being frozen in liquid nitrogen and set on fire. How does any material survive that?
Well, the physics detailed in rocket propulsion elements explains exactly why seals are the Achilles heel here. To prevent high-pressure fluids from leaking out of a valve or a pipe flange, engineers typically rely on elastomeric seals, specialized polymers, or rubbers.
Right, they squish into the gaps.
Exactly. An elastomer functions by deforming under pressure to feel the microscopic imperfections in the mating metal surfaces. But polymers rely on molecular mobility to remain flexible.
So they need heat to bend.
Precisely. The long chain-like molecules of the polymer need thermal energy to slide past one another. When you introduce a cryogenic fluid, like subcooled liquid oxygen, you strip that thermal energy away.
And it freezes solid.
The polymer drops below its glass transition temperature. The molecular chains lock rigidly into place, so the seal no longer behaves like rubber, it behaves structurally like glass.
Oh, wow.
And if you apply a 4,000 psi pressure spike to a glass ring, it doesn't deform, it fractures.
And the moment it fractures, you have a microscopic leak path. Highly pressurized, highly reactive, liquid oxygen bleeds into the engine compartment, which is, packed with ignition sources.
Just waiting for a spark.
The 2026 report highlights China's Long March 5 static test anomaly in 2017 as just a pristine example of this mechanism.
Yeah, the YF-73 engine failure on the Long March 5 perfectly illustrates the danger of prolonged cryogenic exposure combined with high pressure.
What exactly happened there?
The report outlines that the specific synthetic polymer blend used for the liquid oxygen seal ring simply could not maintain sufficient elasticity at that extreme low temperature boundary during a sustained static firing.
So it stayed too cold for too long.
Exactly. The material underwent the glass transition, embrittled, and failed under the sustained pressure gradient of the turbopump. The resulting leak led directly to a catastrophic pad explosion.
But the paradox here is that you can't just synthesize a softer polymer with a lower glass transition temperature, because the other side of the engine is trying to melt the vehicle.
Right, you fix one problem and create another.
The report contrasts the Long March 5 failure with the Long March 7 incident in 2016, involving the YF-100 engine. In that case, the vehicle exploded due to the exact opposite thermal extreme.
Correct. The Long March 7 anomaly originated from a fuel valve seal that degraded under immense thermal load.
So it got too hot.
Yeah. The localized heat flux in that specific area of the engine architecture exceeded the ablation threshold of the seal material. The polymer carbonized, essentially burning away, which destroyed its ability to maintain a pressure barrier.
That really highlights the impossible demands placed on these materials.
It does. I mean, the ideal rocket seal needs the extreme low temperature flexibility of silicone, combined with the structural rigidity of steel and the thermal resistance of a ceramic.
Which obviously doesn't exist.
Since that magic material does not exist, engineers are constantly forced into highly precarious compromises.
I want to look closely at one of the most complex, multi-layered material failures in recent aerospace history, which the report covers extensively. The SpaceX Falcon 9 anomaly in 2016.
Oh, that is a classic case study.
It's fascinating because it didn't even happen during the static fire itself. The engines weren't even running. The explosion occurred during the propellant loading sequence, which makes the mechanism of failure completely different from a heat or pressure blowout in a combustion chamber.
The Falcon 9 anomaly is a masterclass in how unexpected physical interactions in extreme environments can bypass all theoretical safety margins.
So how did it happen?
To understand the failure, we have to look at the architecture of the upper stage. Inside the main liquid oxygen tank, SpaceX utilizes composite overwrapped pressure vessels, or COPVs.
Right, these are the tanks that hold the high-pressure, ultra-cold helium. And that helium is used to physically push the propellants down the feed lines into the turbopumps.
Yes. A COPV is a remarkable piece of engineering designed to minimize mass. It consists of a thin internal dome made of spun aluminum, the liner, which is then tightly wrapped in miles of carbon fiber composite.
So the aluminum stops leaks, and the carbon fiber gives it strength.
Exactly. The aluminum prevents the helium gas from permeating out, while the rigid carbon fiber provides the structural strength to contain the massive internal pressure.
Okay, so during the countdown sequence for the static fire, they were pumping subcooled liquid oxygen into the main tank, completely submerging these COPVs. And here is where the thermodynamics create the trap.
The coefficient of thermal expansion for aluminum is vastly different from that of carbon fiber.
Meaning they shrink at different speeds when they get cold.
That differential was the root of the trap. As the subcooled liquid oxygen flooded the tank, it rapidly chilled the COPVs. The internal aluminum liner contracted significantly due to the extreme cold.
But the carbon fiber didn't.
Right. However, the carbon fiber overwrap, due to its specific woven structure and material properties, did not contract at the same rate. This differential shrinkage caused the aluminum liner to pull away from the inner wall of the carbon fiber shell, buckling slightly.
It created microscopic voids, like these tiny interstitial spaces between the metal and the composite weave. And because the COPV was submerged, the liquid oxygen seeped right into those newly formed gaps.
It seeped in and it became trapped.
Oh, man.
The next phase of the loading sequence involves highly pressurizing the helium inside the COPV. As the internal helium pressure skyrocketed, it forced that buckled aluminum liner to violently snap back out to its original shape, pressing hard against the carbon fiber shell.
But the liquid oxygen was now trapped between them.
Exactly. You now have subcooled liquid oxygen, which is one of the most powerful oxidizers on Earth, trapped between a sheet of expanding aluminum and a rough matrix of carbon fiber.
And carbon fiber is essentially pure carbon, which is an excellent fuel.
Yes. As the aluminum pushed outward under massive pressure, it rubbed against the carbon composite. The friction generated by that microscopic mechanical movement under immense normal force created localized heating.
It's basically the tribological equivalent of striking a match, but the match is surrounded by high-pressure liquid oxygen.
It's exactly that. The friction ignited the carbon fiber matrix, breaching the structural integrity of the COPV. The high-pressure helium instantly decompressed, tearing the liquid oxygen tank apart and mixing the oxidizer with the RP1 kerosene fuel in the lower tank.
Which resulted in the total destruction of the vehicle.
Just a massive fireball. It is a stunning example of how a failure mode can hide in the microscopic interactions between materials.
Because the structural design of the COPV was perfectly sound on paper, right?
Completely. The materials were rated for the pressures. It was only the highly specific operational sequence, the extreme rate of chilling, combined with the specific pressurization timeline that created the conditions for ignition.
It just makes you question how any material survives this stuff. And sometimes the failure isn't even a complex chemical ignition in a microvoid. It is pure, blunt, kinetic force.
Which brings us to vibration.
Right. The 2026 report points to the Starship SN4 static fire in 2020. In that instance, a methane feed line simply disconnected from the vehicle. It didn't melt, and it didn't freeze. It just rattled itself apart.
This brings us back to the acoustic energy we discussed at the beginning. The vibration generated by a rocket engine is not random noise. It contains specific, powerful frequencies.
Like musical notes almost.
Kind of, yeah. If we look at the physics of thermoacoustic instability, the immense energy of the exhaust plume creates pressure waves that travel back up through the structure of the vehicle.
I like to think of it like running a wet finger around the rim of a crystal wine glass. If you hit the exact resonant frequency, the glass absorbs that kinetic energy until it physically shatters.
That's a perfect visualization.
Except in this case, the wine glass is a massive steel pipe carrying highly pressurized liquid methane, and the finger is the acoustic shock wave of millions of pounds of thrust bouncing off the launch pad.
That is an excellent analogy. Every physical component on the rocket has a natural resonant frequency. During the SN4 static fire, the acoustic environment created a standing wave that perfectly matched the resonant frequency of the quick disconnect mechanism on the methane line.
It hit the exact wrong note.
Exactly. The continuous input of kinetic energy caused the mechanism to experience extreme fatigue cycling in a matter of seconds, leading to a catastrophic mechanical separation.
The line just severed.
It severed, dumping massive quantities of liquid methane directly onto the hot exhaust trench, triggering an immediate conflagration.
This issue of acoustic and dynamic pressure isn't just limited to external plumbing either. The report brings up the European Vega C failure in 2022. While this occurred during flight and not a static fire, the mechanism of material failure under extreme dynamic flow is identical. The failure originated in the throat insert of the Zafiro 40 solid rocket motor.
The throat of a rocket nozzle is the critical choke point. It is the narrowest section where the internal subsonic gases are accelerated to supersonic velocities.
The bottleneck.
Right. Because of this constriction, the throat experiences the absolute highest heat flux and dynamic pressure of the entire engine system. To survive this, engineers use advanced carbon-carbon composites.
Which are materials originally developed for the leading edges of hypersonic reentry vehicles.
Exactly.
Now, carbon-carbon is incredibly resilient. It doesn't melt in the traditional sense. So how does it fail? The report notes that the specific batch of composite used for the Vega C throat was too porous.
Yes.
But I want to unpack the physics of that. How does microscopic porosity destroy a material meant to withstand thousands of degrees?
It comes down to the internal ballistics of the exhaust flow. In a perfect, non-porous material, the supersonic exhaust gases flow over the surface. The heat transfer is strictly conductive and convective at the boundary layer.
It glides right past.
Exactly. However, if the carbon matrix has microscopic voids, if it is highly porous, the high-pressure exhaust gas doesn't just flow over the surface, it penetrates into the material lattice.
So it's forcing 3,000-degree highly pressurized gas inside the actual physical structure of the component.
Exactly. And when that gas penetrates the pores, it creates internal stagnation pressure. You now have immense outward pressure acting from inside the material itself, while the external surface is being subjected to extreme shear forces from the supersonic flow.
That sounds like it would just tear itself apart.
It does. The tensile strength of the carbon lattice is exceeded, and the material begins to spall. Microscopic chunks of the composite violently break off.
And this accelerates the ablation process exponentially, right?
Yeah.
As the material chunks off, the throat widens.
And as the throat widens, the chamber pressure drops.
And in a solid rocket motor, chamber pressure dictates the burn rate.
Exactly. The drop in pressure led to an irrecoverable loss of thrust, resulting in the loss of the mission.
So how do they fix it?
The fix required a total overhaul of the manufacturing process, specifically the chemical vapor infiltration used to build the composite, to ensure a denser, non-porous matrix capable of resisting that internal gas penetration.
Okay, so if we accept that these extreme thermal gradients and dynamic pressures are physically unavoidable, it feels like engineers are backed into a corner.
It definitely feels that way sometimes.
You can't change the thermodynamics of liquid oxygen.
Right.
You can't stop the exhaust gas from being highly pressurized. So how do you fundamentally change the architecture holding it all together?
Well, this is where we get into the engineering philosophies.
Right. The 2026 report and rocket propulsion elements outline two distinct philosophies for fixing these vulnerabilities: redundancy and simplification. I want to start with redundancy, because intuitively, if a seal might fail, adding a second seal seems logical.
Redundancy is the foundational bedrock of traditional aerospace engineering. It is the architectural assumption that every component will eventually fail, and the system must be designed to survive that failure.
Just assume it's going to break.
Exactly. Rocket propulsion elements heavily emphasizes this approach. You eliminate single points of failure through duplication.
For example, if a check valve is responsible for preventing high-pressure combustion gases from flowing backward into a volatile fuel tank, you don't just rely on the finest check valve ever manufactured.
No, you place two independent check valves in series.
So if a microscopic piece of debris prevents the first valve from seating perfectly, the second valve arrests the reverse flow.
Exactly. And it extends to the avionics as well. You don't rely on a single pressure transducer to monitor the combustion chamber. You use three, wired into a triple modular redundancy architecture.
Oh, the TMR setup.
Right. The flight computer constantly compares the telemetry from all three sensors. If one sensor abruptly reports a massive pressure spike while the other two report nominal pressure, the system utilizes a voting logic algorithm to determine that the dissenting sensor is faulty.
It essentially outvotes the broken sensor.
Yep. It ignores its data and continues the burn.
But I look at that approach and I see a massive flaw. Every time you add a redundant valve, you add mass. Every time you add a sensor, you add wiring harnesses, data acquisition nodes, and processing requirements.
You are actively increasing the complexity of the vehicle.
Exactly. And in an environment governed by extreme vibration and thermal shock, complexity is a liability.
You have precisely identified the paradox of redundant design. By attempting to engineer the risk out of the system through duplication, you drastically increase the number of potential failure nodes.
Which leads to the second philosophy highlighted in the 2026 report: system simplification.
Yes. Sometimes the most robust engineering solution is to aggressively remove complexity, even if it requires abandoning highly optimized materials.
The report points directly to SpaceX's pivot during the Starship development program as the prime example of this. Initially, the architecture called for the vehicle to be constructed out of advanced carbon fiber composites to maximize the mass fraction.
Meaning making the rocket as light as theoretically possible to carry more payload?
Right. But they abandoned that entirely and pivoted to 304L stainless steel.
It was a shocking pivot to the traditional aerospace community, but when viewed through the lens of simplifying failure modes, it is profoundly elegant.
How so?
Well, carbon fiber composite, as we saw with the COPV failure, is incredibly sensitive to thermal shock and requires complex bonding techniques. Joining a carbon composite tank to a metallic engine structure requires heavy, intricate bolted flanges and specialized elastomeric seals.
And every one of those joints is a leak path waiting to happen under cryogenic cycling.
Exactly. But with austenitic stainless steel, you bypass the thermal limits of composites and the sealing complexities entirely.
Because the metallurgy of 304L stainless steel is uniquely suited for this environment, right?
It is. It has a face-centered cubic crystal lattice structure. Unlike standard carbon steel, which undergoes a ductile to brittle transition and shatters like glass at cryogenic temperatures.
Which is terrifying.
Very. But 304L stainless steel actually increases in tensile strength when exposed to liquid oxygen or liquid methane while retaining its ductility.
It gets stronger when it freezes.
Oh.
And crucially, it has an exceptionally high melting point, allowing it to survive the thermal backwash of the engine plume far better than composite resins.
And most importantly, it solves the seal problem. You don't bolt stainless steel segments together with rubber O-rings, you weld them.
You fuse the metal at a molecular level, creating a monolithic structure.
You eliminate the potential for a seal failure by eliminating the seal itself. Yes, the vehicle suffers a significant mass penalty compared to carbon fiber, but the exponential increase in structural resilience and the drastic reduction in mechanical complexity create a far more robust system.
And that monolithic strength is vital for surviving the chaotic internal physics of the engines themselves. Rocket Propulsion Elements discusses a phenomenon called popping, which seems perfectly suited to destroy a highly complex, fragile system.
Oh, popping is wild. It's a severe form of thermoacoustic instability, primarily observed in engines utilizing hypergolic propellants. Even during a steady-state burn, the combustion is never perfectly uniform.
It's not just a smooth fire.
No. The liquid fuel and oxidizer are injected into the chamber as finely atomized droplets. Due to turbulence, pockets of these unmixed droplets can accumulate within the combustion zone.
And when those localized pockets finally mix, they don't just burn, they detonate.
They detonate violently. The text outlines that these localized explosions produce pressure rise times on the order of microseconds. The resulting shock wave creates pressure spikes that can reach 7 times the normal operating pressure of the chamber.
7 times the pressure in a microsecond.
Exactly. No active control system, no redundant sensor array can detect and react to a microsecond pressure spike. By the time the transducer registers the event, the shock wave has already slammed into the chamber wall.
How do you survive it?
The only defense against popping is pure, simplified structural mass. The combustion chamber must be forged thick enough, and the weld must be strong enough to absorb a 7x overpressure event without rupturing. A highly complex, mass-optimized composite structure might shatter under that localized kinetic impact.
Okay, I want to pivot here. We've heavily analyzed the physical hardware, the metallurgy, the polymers, the fluid dynamics. But modern rockets aren't just flying pressure vessels, they're flying supercomputers.
Very true.
If a physical valve is lagging, or if a harmonic resonance is building up, shouldn't we be leaning entirely on the predictive software to abort the test? If a pressure transducer sees a deviation, a computer can shut the flow down in a millisecond, long before the metal yields. Why do software and control logic fail to prevent these explosions?
Because software is bound by the specific logic parameters defined by its human programmers, and it operates blindly within those parameters.
It only knows what we tell it.
Exactly. The 2026 report explores how procedural and logic errors frequently turn minor hardware anomalies into total vehicle losses. To understand this, we have to look at the infamous Ariane 5 disaster in 1996.
Ah, yes.
While it was a flight failure, the software mechanics perfectly illustrate the vulnerability of control systems.
The Ariane 5 failure is legendary in computer science. The root cause was a single floating point exception, right?
Yes. The rocket relied on an inertial reference system, a highly precise array of ring laser gyroscopes and accelerometers to calculate its exact position, orientation, and velocity in three-dimensional space. The software operating the system was directly ported over from the older, slower Ariane 4 rocket.
Which seems like a logical efficiency. If the code works perfectly on the old rocket, why rewrite it?
The flaw lies in the physical differences between the vehicles. The Ariane 5 had significantly more powerful, solid rocket boosters, meaning its horizontal acceleration profile was far steeper than the Ariane 4's.
It was just a much faster rocket.
Right. The legacy software contained a specific block of code responsible for aligning the inertial platform. Within that code, the system attempted to convert a 64-bit floating point variable representing horizontal velocity into a 16-bit signed integer.
For those who don't write code, the 16-bit signed integer can only hold a maximum value of 32,767. Because the Ariane 5 was accelerating so rapidly, the actual horizontal velocity value quickly exceeded that maximum limit.
The data literally could not fit into the memory space allocated for it.
That is the definition of an integer overflow.
And when the overflow occurred, the software generated an exception. Because there was no specific error handling code written to manage this particular exception, the system defaulted to a catastrophic failsafe.
What did it do?
The active inertial reference system shut down and dumped its internal diagnostic data into the main flight control telemetry channel.
Oh, no. So the main flight computer, expecting navigation data, suddenly received a stream of raw diagnostic code.
And it interpreted that diagnostic code as valid flight data. The main computer calculated that the rocket had abruptly veered 90 degrees off course.
Which it hadn't.
Right, but the computer didn't know that. It immediately commanded the massive engine nozzles to gimbal to their maximum limit to correct the non-existent deviation. The aerodynamic forces generated by that violent, erroneous maneuver instantly tore the rocket to pieces.
A simple software copy-paste error bypassed millions of dollars in physical hardware redundancies.
Yes. We see that same vulnerability in more recent systems, too.
Yeah, the report mentions the Starship SN-10 landing failure in 2021. The hardware survived the descent, but a control algorithm error ingested faulty telemetry regarding the helium pressurization system, leading it to command a thrust profile that was far too low.
And it just hit the ground too hard.
Exactly. The vehicle impacted the pad at high velocity, crushing the engine skirts and rupturing the fuel lines, leading to a post-landing explosion. The math dictated the failure.
This raises an important question, though. What happens when the computer actually gets the math right?
What do you mean?
What happens when the automated health monitoring system works perfectly, detects an anomaly, and aborts the test, but the humans simply refuse to accept the data?
Oh, man. This is perhaps the most insidious cause of catastrophic failures, and the 2026 report highlights a chillingly recent example. The Blue Origin New Glenn static fire anomaly in May of 2026.
This incident is a textbook example of procedural failure and psychological bias overriding rigorous engineering logic.
Walk us through what happened.
According to the preliminary analysis cited in the report, during the countdown sequence for the massive 98-meter New Glenn vehicle, the automated ground control systems detected a pressure anomaly in the cryogenic propellant loading infrastructure.
Okay, so a pressure drop.
Right. The software performed flawlessly. It recognized that the parameters were outside the established safety margins and triggered an automatic hold, pausing the countdown.
The computer did its job. It raised its hand and flagged the vulnerability.
It did. However, the human operators intervened. After a brief review of the telemetry, the test conductors made the conscious decision to manually override the automated hold and resume the sequence.
Why? If you have a multi-million-dollar sensor suite designed specifically to detect fatal anomalies, why would you ignore it when it alarms?
It stems from a psychological phenomenon prevalent in high-stakes engineering, often referred to as go fever, or more formally, the normalization of deviance.
Why?
When an engineering team has spent years designing a vehicle and months preparing for a specific, highly publicized test, the internal and external pressure to execute is overwhelming.
You just want to see it launch.
Exactly. If a sensor throws an anomalous reading, there is a powerful cognitive bias to rationalize the data. The operators might conclude, based on past experience or faulty assumptions, that the sensor itself is providing a spurious reading, or that the pressure drop is within an acceptable, unmodeled margin of error.
They convince themselves that the computer is just being overly conservative.
Exactly. In the case of the New Glenn anomaly, that rationalization was fatal. The pressure anomaly was not a sensor artifact. It was a physical manifestation of a failing fluid delivery valve.
So it was real.
Very real. By manually overriding the hold and forcing the ignition sequence, they pushed a compromised system into a high-energy state. The resulting explosion destroyed the entire launch vehicle and severely damaged the ground infrastructure.
It is a stark reminder that the most sophisticated health monitoring system is entirely useless if the engineering culture permits human operators to dismiss its warnings.
And historically, ignoring those warnings or deliberately bypassing established safety protocols to meet a deadline has resulted in consequences far more severe than lost hardware.
Oh, absolutely. The report references the Netherlands catastrophe of 1960, involving the Soviet R-16 ICBM. This is the absolute darkest manifestation of schedule pressure overriding safety.
The R-16 incident remains one of the deadliest days in the history of spaceflight. Over 160 engineers and technicians were killed on the pad.
Unbelievable.
The core cause was a catastrophic breakdown in basic procedural safety. The R-16 utilized highly toxic hypergolic propellants. During preparations for the inaugural test flight, the vehicle was sitting on the pad, fully fueled and pressurized.
Which means it was a live, highly unstable bomb.
Yes. A problem arose with an electrical sequencer responsible for the ignition timing. The absolute fundamental safety protocol for any liquid rocket, especially a hypergolic one, dictates that if a major electrical fault is detected, you must completely defuel and safe the vehicle before attempting repairs.
It seems like common sense.
It is. However, the program was under immense political pressure from the Soviet leadership to launch in time for a national holiday.
The ultimate form of go fever.
Driven by that pressure, the program director, Marshal Mitrofan Nedelin, ordered the technicians to troubleshoot the live electrical circuits while the rocket remained fully fueled. Technicians were swarming the lower stages, bypassing safety interlocks to test the wiring.
Then what happened?
During this unauthorized, highly dangerous testing, an electrical signal was erroneously sent to the second stage engine.
The second stage ignited while still physically attached to the top of the fully fueled first stage.
The hypergolic exhaust from the second stage instantly burned through the propellant tanks of the first stage below it. The resulting chemical detonation was so massive and sudden that it incinerated everyone within the blast radius, including Marshal Nedelin himself.
It stands as the ultimate tragic proof that engineering protocols exist for a reason, and physics does not care about political deadlines.
It is a horrifying reality check. The contrast between the meticulous, microscopic physics of a freezing polymer seal and the macro-level failure of human psychology is staggering.
Which leads us to the final analytical section of the 2026 report. We've examined the physics of why the vehicles explode, the architectural fixes, and the software vulnerabilities. Now we need to examine the aftermath.
Right, what happens the next day?
When a vehicle detonates on the pad, the program faces a critical juncture. How do they recover? The report provides an extensive comparative analysis of the recovery philosophies employed by the United States, specifically focusing on SpaceX and China's national space program.
This comparative analysis is highly instructive because it reveals how different economic models and programmatic goals dictate entirely different engineering philosophies. And it is essential to view these objectively. Neither approach is inherently superior. They are optimized for entirely different outcomes.
Let's start with the U.S. model, driven heavily by SpaceX's approach to the Falcon and Starship programs. The report characterizes their philosophy as fast iteration with acceptable risk. To me, it looks like an economic strategy masquerading as an engineering philosophy.
Well, the economics are the foundation of the philosophy. SpaceX operates under an agile, hardware-rich development model. Because they manufacture vehicles rapidly and relatively cheaply, especially the stainless steel Starship, they can afford to treat the physical rocket as an expendable data-gathering node.
So they accept a high probability of failure during testing.
Because each failure generates high-fidelity empirical data.
If we look back at the Falcon 9 COPV explosion in 2016, the failure was highly complex. Yet the entire Falcon 9 fleet was grounded for barely 6 months. In traditional aerospace timelines, 6 months is the blink of an eye.
It is an incredibly aggressive schedule. They diagnosed the thermodynamic interaction between the aluminum liner, the carbon fiber, and the subcooled liquid oxygen. They modified the cryogenic loading timelines to prevent the temperature differential that caused the buckling, and they redesigned the COPV overwrap.
They implemented the fix and immediately returned to flight.
And the empirical result validates the philosophy. Since that aggressive, fast iteration fix, the Falcon 9 architecture has achieved a reliability rate exceeding 95% across hundreds of subsequent launches.
And we saw this philosophy taken to its extreme during the Starship development campaign in Boca Chica. SN4, SN8, SN9, SN10, they were detonating skyscrapers on the test stand and the landing pad with astonishing frequency.
Because they inverted the traditional cost structure. By utilizing 304L stainless steel, they drastically reduced the capital cost of each prototype. When SN4 exploded because an acoustic resonance shattered a methane line, the financial loss was acceptable.
It's just a water tower made of cheap steel, basically.
Right. And more importantly, the data allowed them to immediately redesign the bracketing and metallurgy of the feed lines for SN5. This rapid, destructive, iterative cycle allowed them to brute force their way through the unknown physical vulnerabilities of the vehicle much faster than predictive modeling ever could.
So what does this all mean? It's the fail fast, break things model applied to orbital mechanics. It's like the difference between spending 10 years building an unsinkable ship versus building 10 cheap ships, watching 9 sink, and figuring out exactly how to make the 10th one perfect.
That's a great way to summarize it.
But the 2026 report rigorously contrasts this with the Chinese approach, specifically analyzing the Long March program. Their philosophy is diametrically opposed. The report defines it as a methodical, highly rigorous pursuit of zero fault.
The zero-fault philosophy is deeply embedded in traditional systems engineering. It operates on the premise that the physical hardware is too expensive and the payloads are too critical to accept failure as a developmental tool.
You can't blow it up to learn.
Right. When China's Long March 5 experienced the catastrophic YF-73 engine seal failure on the test stand in 2017, their programmatic response was vastly different from SpaceX's approach to the COPV anomaly.
They didn't just redesign the specific elastomer seal, update the loading sequence, and roll another rocket out 6 months later.
Yeah.
The report explicitly states the entire Long March 5 program was halted for a staggering 2 years.
A 2-year stand-down is a massive programmatic commitment, but it reflects their prioritization of absolute systemic reliability over schedule velocity.
What were they doing for 2 years?
The Chinese engineering teams conducted an exhaustive, microscopic root cause analysis of the cryogenic failure mode. They concluded that simply patching the existing YF-73 architecture left the system unacceptably vulnerable to similar thermal boundary failures.
So they threw it out.
They made the monumental decision to completely discard the engine and integrate the significantly more advanced and robust YF-100 engine system into the architecture.
They completely redesigned the propulsion core of their heavy-lift vehicle to eradicate a single failure mode.
Yes, and the results of that immense methodical effort speak for themselves. When the heavily modified Long March 5 returned to active service in late 2019, the architecture had been rendered incredibly stable.
So it worked.
It achieved an exceptional success rate and served as the highly reliable foundational capability required to launch China's most complex, massive national payloads.
Like the Tianhe space station modules.
Exactly, and their intricate lunar sample return missions. The rigorous pursuit of zero faults ensured that when the multi-billion-dollar national payloads were integrated, the launch vehicle was as close to mathematically perfect as physically possible.
It perfectly illustrates how your constraints define your engineering. If your goal is to rapidly mass-produce a fleet of interplanetary transport vehicles out of cheap steel, fast iteration is economically viable.
Right.
But if you are launching a bespoke, irreplaceable flagship national asset, like a space station module or a deep space telescope, you absolutely must embrace the zero-fault methodology, regardless of the schedule delays.
Exactly. The global aerospace industry relies heavily on both philosophies, and understanding the physical and economic drivers behind them is critical to understanding the future of the field.
We have covered immense ground in this analysis today. We started with the sheer acoustic violence of the hold-down clamps, diving into the thermodynamic traps of cryogenic loading and the glass transition of polymers.
The microscopic stuff.
We explore the acoustic resonances that shatter feed lines and the microscopic porosity that destroys composite nozzles. We weighed the architectural trade-offs between redundant complexity and monolithic simplification, the catastrophic logic of integer overflows, and the fatal human psychology of go fever.
It's all connected.
Finally, we mapped the economic philosophies driving how the world's space programs recover from the ashes. And this applies to you, the listener, right now. Whether you are managing a project, writing code, or building a business, you have to decide your own philosophy. Do you demand absolute perfection before you launch, or do you accept a few explosions on the test stand to learn faster?
The physics of the problems may change, but the philosophy of how you solve them defines your success. And as we extrapolate these philosophies into the future, the equations become vastly more dangerous. The aerospace industry is aggressively pursuing nuclear thermal propulsion utilizing active fission reactors to superheat propellants for deep space missions. This introduces a chilling variable. How do you safely execute a static fire test when the engine is powered by a live nuclear core?
Oh, wow.
Does the philosophy of rapid iteration and acceptable risk face a hard, absolute limit when an anomaly on the test stand doesn't just result in a conventional fireball, but a localized radiological contamination event? The way we test rockets today might have to fundamentally change tomorrow.
That is a profound physical and ethical boundary to consider. The sheer energy we are attempting to harness on the ground is only going to increase, and the microscopic margins for error are only going to shrink. Thank you for joining us for this extensive deep dive into the engineering, the physics, and the philosophy of rocket static fires. Until next time, consider the immense complexity required just to keep the fire contained.